we continue to talk about trees. Last week we discussed a heavy light decomposition. It's a data structure which allows you to find some function on a path in a tree. So you have some tree, you have two nodes of this tree, you find a path from U to V, and you want to calculate some function on this path. This week we will upgrade this data structure in two ways. First of all, we will add two additional methods to this data structure. We have two additional requests. These requests change the structure of your tree. They called link and cut. So link operation makes the following. You have two separate trees, one tree with root V, so you have some tree with root equal to node V, yeah? And some another tree with node U. So node U is somewhere inside this tree. And when you make link operation, you simply connect this node V to this node U as a child. So you will have this node V connected to U, and this will be a big, nice tree. So link simply connects two trees. You have one tree, you have another tree, you connect this root of your tree to this node of another tree, and you have this one big tree. The second operation is cut. So cut is basically the reverse operation. So cut, just in opposite ways. You have this big tree, you have this node U, you have this child V with its tree. Then you make this cut, so you have two separate trees. You have one tree with node V, and all other nodes are in another tree. It's simply the reverse operation of this operation. And as usual, we want to calculate some function on a path. Just for simplicity, in this lecture, I will assume I will always calculate a function on a path to the root, just for simplicity. You don't need this. If you want to calculate a function on some path from one node to another node, it's also possible. It's quite simple, but I will only consider paths to the root. So I need another function calc for V, and this operation takes a path from node V to the root of your tree. So this is the path, so R is the root of V, and I will calculate some function on this path. So simply return some sum on this path. You have some values in each node. Let's say you have some values in each node when U belongs to path from V to R, like this. So this operation is the same as in the last lectures when we talk about heavy light decomposition. So you have this path in each node. You have some value, and you want to calculate some function on this path, some minimum. I don't know, bitwise end, any associative function. These two operations are new. These two operations change the structure of your tree, right? Basically, you don't have one tree. You always have a set of trees, yeah. And you want to be able to link these two trees or to split two trees, yeah. That's all. That's the whole plan. And the data structure which allow you to do all this operation is linker tree. It's actually one of the coolest data structures in this semester. Again, it was invented by Roberto Jan and Dennis Slater. Like Splay trees. It actually uses Splay trees inside, so if you don't know how to use Splay trees, you may go back to the lecture about Splay trees. We will use Splay trees. Actually, if you don't remember how actually Splay trees works, it's not a big deal. You can watch it later if you forgot how to make Splay trees. You may think about Splay trees like a special binary search trees. You can actually use any binary search trees, but the time complexity will be not that good. Speaking about time complexity, in heavy light decomposition, we learn how to calculate function on a path in log square time. Like, in this data structure, we will upgrade it. We will learn how to make this operation in log n time. And also, both this operation will also work in log n time. So all these three operations will work in log n time. That's all. That's the plan for today. Let's go. So some people are afraid of linked trees. Sometimes it's used even in competitive programming. So in some code forces problem, you may find some problems which require something like that, so like something like linked trees. Some people are afraid of linked trees. It's actually not that difficult in structure. So the algorithm is pretty simple. We will learn how to make all these operations, and the code will be quite small. Now, if you have already implemented your Splay trees, if you already have a Splay tree, additional code is quite short. But time complexity analysis will be quite complicated. So I will spend some time to describe you the algorithm, and then I will spend a lot of time trying to prove you that the time complexity is actually log n. Ready? So let's go. So how the data structure is structured? So you have some tree. Let's build some tree. Let's plan some tree. So we have something like that. Let's have some more nodes here. Maybe it's too much. Let's add one more here. So you have some tree. Again, this is the root of the tree, there's leaves of the tree, as usual, this like normal tree. Let's put some labels. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Cool. So you have some normal rooted tree. What we'll try to do is to make a decomposition of this tree. So we'll decompose this tree into some paths, like in heavy light decomposition. But instead of making some special properties, like in heavy light decomposition, we decompose it into some heavy paths. So we declare some edges heavy, and we try to maintain some special properties, and these properties will help us to make the good time complexity in the end. In this data structure, we will not care about any constraints, so we will make some decomposition. That's the plan. We will build some decomposition and will allow this decomposition to rebalance itself, like in Splay trees. So we will make some operations. These operations will affect this decomposition, and magically, in the end, we will prove that the time complexity will be log n. Absolute magic. So what is decomposition? We will... I need some special word for this. Let's use some marked edge. So for each node v. Okay, yeah, thank you. I really miss these reminders. Yeah, cool. For each node, we will mark one of the children. So each node has some children. So for each node, we will mark at most one of the edges to the child of this node. So one of these edges will be marked. Well, for example, here, and that's all. We'll not put any constraints. Any edge can be marked. For example, in this tree, we will mark, let's say, for this root, let's mark this node, this edge. For this node, let's mark, I don't know, this edge. We'll mark this edge. For this node, for example, we can mark no edges. It's also possible some node may have no marked edges. And for this node, we have this edge, something like that. So that's the perfectly fine decomposition of the tree. So again, why it is decomposition? Because if you look only on these marked edges, then your tree will be splitted into some paths. So you have this path, you have this path, and you have these small paths, like this paths of single node. That's the composition of the tree. Now, we will want to calculate some function on these paths. So, like in previous lecture, on each of these paths, we need to build some data structure which allows us to calculate function on the path, like segment tree. And now it's difficult part. We need to modify this decomposition. So at some point we will need to modify this decomposition. For example, we need to be able to mark the edge or unmark the edge. So if let's see what's going on with this decomposition when we change the state of some edge. For example, if some edge was marked, so if you have some marked edge like this, this marked edge belongs to some path. So have some path going through this edge. What will happen if you unmark this edge? So if you unmark this edge, then you have situation like this. Now this edge is not marked, so you have this part of your path and this part of your path. So simply what's happened is that this path is split into two halves. So you have this part of your path is one segment of your path, and this part is another path. Yeah? So here you have one single path, but after you unmark this edge, you have two separate paths, like this upper part and this bottom part. Now, that's what happened when you unmark some edge. So it was marked, now it's unmarked. So this path containing this edge now split it into two parts. What happened if you mark the edge? Opposite thing happens. So if you mark the edge, then the opposite thing happens. If you have unmarked edge and then you mark this edge, then you need to merge these two paths into one. So you have these two separate paths. After you mark this edge, you have one single path. Cool. That's all. Now, let's combine this. What do we need? For each path, we need a data structure which allows us to make three types of requests. First type request is to calculate function on a path. And second and third are to split the path into two paths or to merge two paths into one single path. So write it. So for each path, so you have this path. Path is just a list of nodes. Yeah, so you have nodes. You need to be able to do three requests. First request is to calculate function on a path. Second is to split the path. So we need to be able to split the path. What's that? Split and merge. Okay, who watched the previous lectures? What data structure do we need to make these three types of operations? Yeah? I already spoiled it, right? I already spoiled it before, but say something. What data structure allows you to make these three operations? Cool, yeah. We simply need any type of mergeable binary search trees, like trees or Cartesian trees or Splay trees. So we need any type of binary search tree which allows us to make splits and merges. For example, trips are already fine. Trips will not give you this time complexity yet, but they are also good. But we will use actually splay trees in this data structure. So we will use splay trees. Now the whole plan. We will build this data structure in the following way. We have this tree. For each node, we will mark at most one of its children. Now the whole tree will be split into paths. For each path, we will build a splay tree. Now we will be able to modify our decomposition. So when we unmark the edge, we simply split this splay tree into two splay trees. When we mark the edge, we merge these two splay trees into one splay tree. That's the whole plan. For example, let's build decomposition for this tree. So for this tree, we have, for example, here we have this path. So for this path, this is the path of 4 nodes. So we need to have a splay tree which contains these 4 nodes in this order. For example, we may have something like that. Let's have 1, 9, 4 and 7. Let's build like this. So this splay tree corresponds to this path. In this path, we have these nodes in this order. We have node 9, 1, 7, and 4 in this order. In this splay tree, we have the same nodes in the same order. So if you iterate all nodes from left to right, you have node 9, 1, 4, and 7. So the order of these nodes is the same as the order of these nodes in this tree. So this splay tree corresponds to this path. Cool. Now here is node 8. Node 8 is simply a splay tree of one node. It's quite simple. Let's move here 8. Now for this path, we need to remember the parent of this path in this whole decomposition. So this path is connected to this node 1. So we'll remember that for this path is connected to node 1. So we'll make special pointer here, like this. This special pointer will say that this tree is connected to this node. Cool? Now let's build it. So here we have node 3. Simply, it's a tree of one node. So we need 3, and it is connected again to node 9. This node 2 connected to node 3. Here we have a path of 3 nodes, 10, 6, and 11. So we built a splay tree of 3 nodes. Let's make something like this. Yeah. It's a nice splay tree. And this path is connected to node 3. So we'll remember that this path is connected to node 3. So we'll make a pointer. Pointer is always from the root of the tree. So we take the root of this splay tree and connect the root of this splay tree to this node 3. And what left? This node 5. We also have this node 5. It's also connected to 3. That's all. So this is the structure of your splay tree. So internal structure of this splay or of your linked cut tree is very simple. You decompose your tree into paths. For each path, you have a splay tree. And from the root of the splay tree, you have a pointer to the node which is attached to your tree. So each path except of the root tree. So each path except of one root is attached to some node of the tree. So this path corresponds to this splay tree. So for the root of this Splay tree, you have a pointer to the node which is attached to your path. That's all. Clear enough? Cool. That's the whole plan. That's how it comes. That's the whole structure actually. Very simple structure. Now, the key operation of this of the linker tree is expose. Let me show it. Expose is very simple operation. So you take this node V. You have this path from V to the root. Expose simply makes all the edges on this path marked edges. So you simply need to mark all the edges on this path. So you have this path. You just need to mark all the edges on this path. You also may detach some paths on those. You also may to unmark all children of the V, just for simplicity. You actually don't need to, but you can. So after you call the expose operation of some node, all edges on the root, on the path from V to the root of the tree will be marked. That's all. That's the whole point of this operation. Cool. Now, how this operation will help us to calculate the function? Very simple way. When you need to calculate function in your linker tree, so you need to calculate function from some node to the root. You take this node, call the expose operation in this node. This expose operation will make all the edges on this path marked. So now all these edges belong to the same path. So this path will be stored in some Splay tree. So in the root of this Splay tree, you will have the result of your function. So to calculate the function in this tree, you simply call the expose in some node, have this path in a single Splay tree, and in this single Splay tree, you find the result of your function. It's that simple. Now, how to make link and cut operation? Link and cut operations are actually pretty simple. So when you link two trees, you simply connect one tree to another tree with some unmarked edge. So you connect it with some edge, and you have this edge unmarked. That's simple. The decomposition will not change. So you simply connect this. No, you need to have some another tree. Yeah, you simply connect it and make this parent link. Select this. So link operation is pretty simple. When you need to link some tree to another tree, you take the root of this tree, connect it to another node. When you need to make cut operation, you just unmark the edge you want to cut. If it is marked, you just unmark it. You can make this split. And then remove this edge. That's all. So link and cuts are pretty simple. When you need to calculate, you make expose and then use this whole path to calculate your function. That's all. No, let's try to expose something. Let's take some node and try to call expose function in this node. For example, let's take this 11. So let's call expose operation for this node 11. How to do it? Very straightforward way. We will iterate over all unmarked edge on this path and make them marked. That's the whole plan. So we will iterate over all these edges and mark all these edges. That's the whole plan. So how to find the closest unmarked edge? It's quite simple. Let's take this node V. This node 11 belongs to some Splay tree, right? To this Splay tree. We need to find the edge, which is this path is connected to some node. So we need to find this node V in this structure. And now find this splay tree and find that this splay tree is connected to this node 3. So the next edge we need to make marked is the edge which connects our path to node 3. It is this edge. So how to do it? Pretty simple. First thing you need to do when you have a splay tree and when you find some node in the splay tree is to make splay operation. So we find this node and make a splay operation in this splay tree. So what happens when we make splay operation? Let's do it. So first we make splay of 11. This is log of expose 11. So what happens when you call expose of node 11? So first you splay this node 11. What happens, so if you remember how splay trees works, you just make one zig operation here, so you need to rotate this edge. So you rotate this edge, now 11 is the root, 6 is here, 10 is here. Nice. Now 11 is the root of the tree. Now you need to find this edge. This edge is simply this pointer to your next to the next node to the node which is attached to your path. So you need to find this. This node is free. You simply take this pointer from here to here, and you know that the next edge connects your path to node 3. So you take this edge. This edge. Yes. So this link corresponds to this edge. You take this edge and you need to make this edge marked. So how to make this edge marked? You need to make the edge marked, you simply need to make merge operation. So you take this node and now you need to merge this tree and this tree. How to merge two splay trees? Pretty simple. You need to splay this node 3. It's simple because it's already root. And now you attach your tree as a right child of this node 3. So you simply take this splay tree, now 3 is the root, you attach your tree as a right child of this 3. So simply make it like this. That's all. Now this edge is marked and you have this path of 4 nodes. Again, now you have this path 3, 10, 6, 11. It's here 3, 10, 6, 11. So this splay tree corresponds to this path. That's all. Now you need to find the next edge you need to mark. This edge will be the edge which connects your path to the next node in this tree. So this edge is simply this pointer. So you need to find this pointer. This pointer corresponds to this edge. Now you need to make this edge marked. How to make this edge marked? No, first, before you make this edge marked, you need to unmark this edge because each node may have only one marked child. Yeah? This node 9 already have this edge marked. So you need to first unmark this edge and then mark this edge. Let's start by unmarking this edge. So first we need to unmark this edge. How to unmark the edge? We need to make split operation. So we need to split this splay tree after 9. So we need to make 9 and everything after 9. How to make this? Pretty simple. How to split splay trees? You call a splay operation of this 9, and you will have something like that. Now 9 is the root of the tree, so to split everything, so everything after 9 is the right branch of this 9. So this right branch is this part of the path after node 9. So this has node 9, and everything after this node 9 is the right branch of this node in this split tree. So to split your split tree, you simply need to cut this right branch. So you cut this right branch. And now you split this path into 9 and 147. So you have this 9 and this 174. My bad, so must be 74. Didn't you notice? You need to pay attention. Sometimes I make stupid mistakes. So you split your path into 9 and everything after 9, and then connect this path with this parent link. So now we simply unmarked this edge. So this edge is not marked. So we have this path and this path. Cool. And now we need to mark this edge. To mark this edge, we simply need to take this splay tree and connect it to 9 as a right branch. Again, so all these nodes must go after node 9. So we take this node 9 and connect this whole tree as a right branch of this 9. So we take this tree and connect it as a right branch of this 9. Let me move 9 here. So this 3 will be a right branch of this 9. Okay, this picture is a little bit messy, but fine. Like this. That's all. Now this edge is marked. That's the whole function. So in the end, after we call the expose of this node 11, this whole path from the root to 11 is contained in this one single split tree. So this split tree corresponds to this path from 9 to 11. Again, let's check. So in this path we have nodes 9, 3, 10, 6, and 11. And here we have 9, 3, 10, 6, and 11. In the correct order. So the order of these nodes, again, from left to right, is the same as the order of these nodes from root to the left. You're not asking anything. That's dangerous, actually. Either you don't understand anything or you understand everything. That's suspicious. Okay. That's all. That's all. That's the whole function we need, actually. Let me write some code. So, what happens when you call expose function of node v? So you take the node v, call the splay of this node. Then you make, so you have this node v corresponds to some, belongs to some path. So you need to find this node to node u. So you need to find this edge. This edge, you immediately call splay to node v. Now v is the root. So this node v, you simply get by using this link. So you use this parent link of node v. There is a special term for this, but I don't remember this. Like path parent, something like this. That's all. Now you need to take this node u. This node u belongs to some path. First, you need to split this path after node U. So, to split this path after node U, you first call Splay of node U. Now, this part is simply the right branch of U. So you take the right branch of U. This double. Now you need to split your splay tree after node U. You can split your splay tree by simply removing the right branch. So you remove the right branch. Let's say parent. And parent of W will be U. So again, you take this W, you split your splay tree after node U, like this, and connect this W to U using this. And here also you have this link, and here you have this link. Now you simply have both this path connected to U using these parent links. And now you make this edge marked by simply connecting your splay tree of node V to the splay tree of node U. You simply need to connect it as a right branch. You know that there is no right branch right now, so you simply connect as a new right branch. You may simplify this, but I will know. So here you disconnect. This is the split, yeah. And now you connect your node as a reference. So this is true. And let's remove the parent here. That's all. Now this edge is marked. So you simply connected these two paths into one big path. That's all. And now you do the same for node U. And just put it into while. You do it while you have a parent. That's the whole code of the linked tree actually. So if you already have a splay tree implemented, yeah. So first, if you want to implement this, first try to implement splay trees. It's not that complicated. You need to implement all these zig operations, zigzag, zig. Every operation is just like 5 lines of code. It's pretty simple. And now when you already implemented these splay trees, that's the whole code you need to add to implement linked trees actually. So it's quite simple data structure. Try not to be afraid of this. So it may be hard to debug, so maybe I put some bugs here. Some minor bugs. For example, here you may have no right child. If this W is null, then here you will have null pointer exception. Small bugs, but you will fix them. The idea of this code is that simple. So you can just implement it and then run some stress tests, debug it, and so on. That's not that bad. So that's all. That's how you make expose. And that's all you need. So when you need to calculate function, you call expose again. You call expose. Now this whole path is a single splay tree. The root of this splay tree will contain the function of this path. That's all. Cool. And now I will spend the rest of this lecture to prove that the time complexity is actually as expected. So let's go. Now it's time to prove the time complexity. Maybe we'll have some more examples before, no? Do we need some more examples of expose function? Yeah? 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 Anyone? We may call it like expose for some normal. No? Don't need to. Because I'll need to erase everything. I will not draw back. Okay. So let's make one more, okay? Let's make one more. Let's call expose, for example, for this node 5. So what's happened when we call expose for this node 5? We call expose for this node 5. We need to connect this 5 to this Splay tree of containing this path. So this node 5 is here. It's connected to 3. So we need first to call Splay for this 3. Now this 3 will be the root. And this 9 will be below. So this connected to 3, this connected to 3, this connected to 9, this connected to 9. Now we detach this right child. Now again, we split this tree into two trees. First is 9, 3. Second is 10, 8, 11. And 6, 11. And now we attach this 5 as right child of 3. Like this. That's all. In the end, we have situation like this. So you have this path, 9, 3, 5. It's here, 9, 3, 5. It's a path which is in this Splay tree. Cool. Let's go. Let's go to some time complexity analysis. Cool. So now I will try to prove that the time complexity of this expose function is log n. Actually, not the actual time complexity, but the amortized time complexity. So amortized time complexity of this expose function is log n. Again, let's remember, what is amortized time? Amortized time means that some operations may take longer time, but if you make a series of operations, then the total time of your of all of these operations will be normal. So if you start with some starting position, when, for example, start position when you have like single nodes, so each single node is a separate linked tree, and make series of operations. You make operations let's make O2. O3 and so on, OM. So you make M operations in series and try to calculate the total time of all these operations. It will be no more than some constant by M log n. That's what this amortized cost means. Yeah. And I will prove this using potential method like before. So we will introduce some potential function. And we will define the amortized time as the sum of actual time plus change of the potential. And then we will prove that amortized cost will be log n. What does it mean? It means that if you have a series of operations, then the total amortized time will be no more than Cm log n. And this total amortized time, here, is total time plus change of potential. So this is greater than 0, so it's greater or equal than the total time. So we will prove that we will introduce some potential function. That's the key. That's the key idea of all this amortized analysis. You need to introduce some good potential function, and using this good potential function, you prove that the amortized time complexity is log n. And if you prove this, since this potential is non-negative, then this total total amortized cost is greater or equal than your total cost. Yeah? Because your amortized cost is sum of your actual cost plus change of potential. So if we prove that the amortized cost is less than m log n, then the real cost will also be less than m log n. Because total amortized cost is always greater than the total real cost. So that's the real cost of your operation. That's the amortized cost. Cool. We already discussed this before, so it's just, if you're not familiar with all this amortized analysis, you need to go back to the previous semester when we discussed some amortized cost. Go. So now we'll need to introduce a good potential function. How to introduce good potential function? Let's start from this. First, let's prove the log square. So first, let's prove this bound of the time complexity. So let's first prove that the amortized time is no more than log square. It will be a little bit simpler and doesn't require any Splay tree magic. So first let's prove this. I forgot the word. So let's prove this time complexity. How to prove this time complexity? Let's use the following potential function. So let's say that the potential function is the number of heavy unmarked edges. Multiplied by log n. What does it mean? Let's look at some tree. We have some tree. In this tree, we may build some heavy light decomposition, like in previous lecture. We will not build it in this algorithm. In this algorithm, we don't need any heavy light magic. But for this analysis, let's imagine we have some heavy light decomposition. So you have some heavy light decomposition. Some of the heavy edges are marked, so some of your heavy edges belong to your decomposition, some not. So let's look at all heavy edges which are not marked in your decomposition. So this potential will be just number of these edges. Let's draw some. Let's try have some more tree. Let's have something like that. Imagine you have some tree and you have some decomposition of this tree. So your Linka tree may build any decomposition of your tree. Yeah? So you may call these exposes in some order, so any decomposition is possible. For example, you may have something like that. You may have this edge, let's say this edge, and also this edge and this edge. So you have some decomposition of your tree. Something like that. Now let's build some heavy light decomposition. For example, for this node, heavy edge is the left one. So this edge is heavy. This edge is heavy. Now any of these, well, let's say this edge is heavy. So any of these two edges may be heavy. Here this edge is heavy, this edge is heavy, and let's say this edge is heavy. So these red edges are heavy edges. And these purple edges are the edges marked in our decomposition, in this decomposition. So let's try to calculate the number of heavy edges that are not marked. For example, this edge is heavy, but it's not belong to our decomposition. This edge and this edge. So these three edges are heavy edges not marked in our decomposition. So the potential of this tree is 3 log n. Cool. That's all. That's how we define the potential function. Now, using this potential function, I will prove that the amortized time complexity is log n, log square right now. We will later upgrade it to log n, but now let's prove that it's log square. How will prove this? Very easy. Let's calculate the real time of this operation. So, what is the real time of this expose operation? Let's see. We have this expose function here. It's quite simple. So what is the time complexity of this operation? What is the real time complexity? So how many operations do we make in this in this function? Let's use this. So in this function, we have some number of these loops. So we have this while loop. Yeah. What is time complexity of single iteration of this while loop? Isn't too fast. Let's stop here for a little. So I want to calculate the real time complexity. So the real number of operations we need to implement this expose operation. Yeah. So this expose operation consists of several iterations of this while loop. So on each iteration of this while loop, what is time complexity of all operations inside? Let's wait. First let's mark all the simple operations. So these are simple operations. So we have one operation here, 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 one operation here. So all these operations cost you constant time, right? So these all are just basic operations. You take some pointer, assign some pointer, and so on. Yeah? So all these operations actually have constant time complexity, right? What about this Splay operation is the only complicated operation in this whole loop. So all operations except this Splay are pretty simple operation. You just assign some value or get some value. Very simple. What about this Splay operation? What is the time complexity of this Splay operation? I'll wait. Say something. So again, on each iteration of this while, we simply mark one of the edges in our decomposition. So we take the closest unmarked edge and mark this edge. So to make to mark this edge, we simply need to make split of two Splay trees and then merge these two Splay trees. You scare me. What? Where is everybody? Is it too complicated? Cool, at least one. Nice. Splay operation actually takes log n time. Whew, thank you. I was worried. That's fine then. Splay is one operation of Splay trees by basic operation. So all other operations depends on this Splay operation. So actually it takes log n time to call Splay operation in a Splay tree. Now each loop of this, or each iteration of this loop costs you log n time. So what is the total time complexity of this expose? It actually depends on the number of edges you need to mark. So if you have this path from V to root, on this path you have some edges are marked, some edges are unmarked. So you have these edges are marked, these edges are marked. So you have this part plus this part plus this part plus this part. So the time complexity depends on the number of edges you need to mark. Let's say you have k edges here. So let's say you have k edges on this path which need to be marked. So to mark all these edges, you need to spend log n time for each edge. So the time complexity of this expose will be k multiplied by log n. Right? That's all. Now, what is the change of potential? Well, let's see. The potential is the number of heavy unmarked edges. So how this potential will change if we mark some edges on this path? Will it be increased or decreased? Simple question. So we're looking for the number of heavy unmarked edges. Yeah? So edges like this. So they are heavy edges, but these edges do not belong to our decomposition. So if we mark all these edges on this path, will potential increase or decrease? I'll wait. Okay, to answer this, you don't need any information from the previous lecture. You just need to understand what's going on. So if you take some node and mark all the edges on this path, and potential is number of heavy unmarked edges. So will the number of unmarked edges decrease or increase when you mark all the edges on this path? Okay, let's make it more simple. Imagine you have heavy edge here. If you have heavy edge, you call expose of this V. So now this heavy edge is unmarked, and when you call expose, you will mark this edge. So what happened will be potential function. Yeah? So if you mark this heavy edge, how it will affect the total number of unmarked heavy edges? Okay, that's simple. Maybe I'm doing it a little bit too fast. Again, I will repeat it until you get what's going on. Again, this potential function is simply the number of heavy unmarked edges. So you have your tree, you have some edges marked and some edges are not marked. you find some heavy edges on your tree. And this potential equals to the number of these unmarked edges. So if you have some heavy edge here, and now it is unmarked. But when you call expose of this node V, you will mark all the edges on this path, especially you will mark this edge. So it was unmarked and now it's marked. So how it will affect the total number of unmarked edges? Oh, you scare me. Okay, try to guess. You're just kidding, right? Oh, once again, once again. Again, let's take this. Let's take this tree. Now potential is free, yeah, because we have 3 unmarked edges. So we have 1, 2, 3 heavy unmarked edges. If we call expose, let's say for this node, so if we call expose for this node, we will this node will be unmarked and this node will be marked. Edge will be marked. Don't be scared. Just say something. 10 viewers are enough. At least one of you will guess correctly. Well, only 2 options. It will be decreased or increased. So you need to guess one of 2. So if there are 10 viewers, the probability that none of you will guess is actually quite small. So at least one of you will guess and will look like a smart guy. Again, I call expose for this node. Yeah, potential function was free, and when this edge is marked, yeah, the total number of unmarked edges will be 2, right? You're scaring me. You don't need to be scared. I need to be scared because. That's not good. That's not good. It is decreasing. Oh, at least 1. So yes, you're really MVP of this lecture. Yeah, I agree. So when you have heavy edge on this in this thing, you will decrease the potential. Yeah, because this edge is now marked. It was unmarked and now it is marked. So before we call this exposed, it was counted in this number of heavy unmarked edges. And now when we call this expose, this edge is marked, so potential is decreased by 1. So each heavy edge will decrease the potential by 1. And what if we have light edge? If we have light edge, potential will actually may increase, because if we have another edge, so we have another edge is heavy, and it is marked. So when we mark this edge, we first unmark this edge. So when we have light edge here, we need to unmark this edge. So the number of unmarked heavy edge may be increased. So if we have heavy edge, potential will be decreased. When we have light edge, potential may increase by 1. So the total change of potential depends on number of heavy edges and number of light edges. So let's split this K into 2 halves. So let's say we have X heavy edges and Y light edges. So what will be total change of potential? So when we have heavy edge, we decrease the potential by 1, so it will be minus x. When we have light edge, we increase potential by 1. No, we may increase it by at most 1. Let's see, it's normal. Plus 1. So each heavy edge decrease your potential, each light edge may increase your potential. Log n. Because it's log n here. Well, now let's split this k. So this k is actually x plus y. That's all. Now let's calculate the amortized cost. Total amortized cost will be real cost plus change of potential. So we need to sum this and this. You will have x plus y log n plus minus x plus y log n. Now you simplify this. Here you have x, here you have minus x. So they will be eliminated. So we'll be eliminate this and this. So in the end, we'll have just 2y log n. That's all. That's all. And now I claim that this number is at most log square. Now, why it is so? Because this y is the number of light edges on the path. Number of light edges is never more than log n, because it's heavy light decomposition. So y is never more than log n. Yeah, that's some heavy light decomposition. In any heavy light decomposition, there is no more than y light edges on any path. So you have on this path you have no more than y light edges. So this y is no more than log n. So this is no more than 2 log square. That's all. That's all. That's the whole proof. Too complicated. Again, the idea is that if you make a lot of operations in this loop, it means you mark many edges in your tree. If you mark many edges in your tree, most of these edges will be heavy edges, because on any path there is at most log n light edges. So actually, if you make a lot of operations in this loop, it means you mark a lot of heavy edges in your tree. So your decomposition is closer to the heavy light decomposition. That happens. No, you need to, you made, so all lectures are on my YouTube channel, so you can rewatch all the previous lectures. You actually don't need, you don't need previous lectures here. Okay, you may need, you may need to know how this binary search trees works, but that's all. Yes, and about heavy light decomposition, yes. If you missed previous lecture, you may be not familiar with heavy light decomposition. So what is heavy, what is light edges? So you may need to rewatch the previous lecture about heavy light decomposition. That's fine. Oh, that's almost all. Now we need to prove the final time complexity. So here I prove the time complexity is log square, but it is actually not log square, it's actually log n. Let's prove this. To prove this, we need to go deeper in the Splay trees. In the Splay trees, time complexity of this Splay operation is actually not log n. It's not log n. It's 1 plus the change of the potential. So it's 1 plus change of potential of this, change of rank. So if you watch lecture about Splay trees, maybe you remember something like that. So the actual time cost of Splay operation is not always log n, but it is the difference of the ranks of the node before and after your Splay operation. We proved this when we learned about Splay trees. So what we'll do, we will use this time complexity bound to prove this time complexity. To do this, we will simply more carefully calculate the total time cost of this operation. So, what is the total time cost of this operation? Let's look on all nodes we make Splay in this loop. So what happens in this loop? We make Splay of node U when we make another loop. Again, take the node U, make Splay, and so on. So if each Splay costs you some change of this string. So yeah, let's do it like this. Second operation costs you change the rank of a second U. And so on. So the total time complexity is actually can be calculated as sum of these. So this U1, U2, U3 is variable U on different iterations of this loop. So on first iterations we have U1, so actually it's these nodes. So this is U1, this is U2, this is U3, and so on. So when we call expose, we first go to this U1, Splay this node, then go here, Splay this node, then go here, Splay this node, and so on. Let's calculate total time complexity of all these Splay operations. Is this? So this is time complexity of first Splay operation, time complexity of second Splay operation, third Splay operation, and so on. Now let's calculate this sum. So this sum is pretty simple. So sum of these ones is k, because we have k operations here. And sum of these changes is actually no more. This sum is actually no more than difference of final rank of last node minus first rank of the first node. It's just like telescopic sum, so these sums stack together in one big sum. This happens because the rank of each next node is no more than the rank. The rank of the previous node is no more than the rank of the next node. Rank of new rank of UI is no more than old rank of UI plus 1. So each new node you need to Splay have greater rank than the previous node. So you take Splay this node, then Splay this node, then Splay this node. So each new node will have greater rank than the previous node. We need to introduce good ranks for this, but we'll do it. In this sum, you can take this new rank of U1 and previous rank of U2 and just eliminate these two. And then you eliminate these two, and so on. So in the end, you only left with the last rank of the last node and first rank of the first node. So you have this difference of two ranks. And this difference is log n. Okay, this looks like magic. This may look like a magic, okay. So again, what I try to do, I'm trying to calculate this time complexity more carefully than just sum all these log n operations. It actually turns out that it's never possible that all these Splay operations work in log n time. If you have series of these Splay operations, the total time of all these Splay operations is no more than k plus log n, not k multiplied by log n. So the actual time cost is k plus log n. Because you use Splay trees. And means here you have x plus y plus log n. So now you just remove this log n from here. Just from here, remove it from here, and in the end you remove it from here and from here. You just plus log and shift. Something like that. Like this. That's the whole idea. Okay, that's complicated stuff. I know. I agree. That's not the simplest data structure in this course, of course. Last thing. I need to prove this actually. Let's prove this just to make this lecture complete. Let's prove this. To prove this, I need to introduce a good potential function for the Splay trees. Let's remember how this rank is calculated in a Splay tree. In a Splay tree, rank of the node is simply logarithm of sum of all weights of u in subtree of v. So we have node v, we have its subtree, we calculate total weights of all nodes in this subtree, and rank is just logarithm of this value. So to make this true, we actually need to introduce good weights for all nodes. So the weight of the node, if you take node v, the weight of this node will be total number of all nodes connected to this node using these parent links. So you have this node v, you have some trees connected to this v using these parent links, and something connected to here else. So let's say that the weight of this node equal to the total number of nodes connected to this node using these parent links. That's all. Okay, that may look scary. And if you introduce weights like this, then the ranks will be up to log n again. And when you go from one node to the next node, so it happens like this. You have this v, you have this u. This u is connected here. Then the weight of this node will actually include total number of nodes in this section. So if node v is connected to u, like here, because u is a parent of v, so u is always the parent of v. So the weight of this node will actually include all nodes in this section. It means that the rank of this node will be greater or equal to the rank of this node. So in this case, the rank of u will be greater than the rank of v. Just because the weight of this node includes all the nodes in this section. That's all. And this actually this proves that this inequation, and this inequation proves you this, and this proves you this, and so on. Okay, this may be a little bit too much for you, but maybe you will rewatch this lecture in a few weeks and understand it more correctly. It's pretty complicated for the first try, so it's not the simplest data structure. So some data structures you need to watch lecture several times to understand what's going on. So if you're not familiar with this Splay trees and so on, you may go back and rewatch the lecture about Splay trees, lecture about heavy light decomposition, and then we simply just combine a few tricks from several data structures. So we combine some tricks from heavy light decomposition, some tricks from Splay trees, and build this whole data structure. That was the whole plan. Okay, that's all for today.